Hello everyone, today we'll talk about microphone design and microphone construction. Okay, so the goal for today's video is to go over microphone design basics to a deep enough level that I think every home recording engineer should understand about microphones. And I'm going to keep the technical details here to a minimum because microphone design can easily turn into an engineering stroke fest. So, really just trying to do the basics here enough for everyone to understand. Okay, so we need to first talk about what is the purpose of a microphone. The purpose of a microphone is to act as a transducer where it is converting acoustical energy in the room into an electrical audio signal. It is very easy for us to forget, especially for those in the DAW world, that sound is not actually an electrical sine wave or some variation of such. In reality, it is a series of air pressure variations that is happening in the air particles around us. For humans, this is picked up by our eardrums, where our brain converts this into intelligible sounds. We mustn't forget that our ears react very differently to sound than a microphone. In tandem with our brain, our ears are the result of millions of years of evolution, and they have been perfected for the uses that humans have needed to survive. The first thing that we need to think about is that our ears and brain are able to filter out and focus on specific sounds. Think about the situation where you're talking to a friend in a room with a radio or a TV playing in the background. We are very easily able to filter out that TV noise and listen to our friends speaking and to be completely focused on what they are saying. A microphone is not going to be able to do that. It is indiscriminate with the sound coming from all directions. It is not able to filter out certain sounds. The second thing I want to talk about is that our ears and brains somewhat act as compressors. On a daily basis, we hear sounds anywhere from the range of 0 dB to about 100 dB, give or take. And, we're able to adjust to those different sound levels at ease. Microphones and their associated equipment are not going to be able to do that. You are going to need to change the gain settings on your mixing board to compensate for different levels of dynamic range when you're recording sound, right? So you need to think about this when you're using a microphone on any source. The third and last thing I'm going to add about the differences between our ears and a microphone is that our brains rely more heavily than you think on visuals for how we perceive sound. The easiest example I could think of is when you're speaking to someone and we rely on lip movements to better understand what we are saying. Our brains can be tricked very easily, whereas a microphone cannot be tricked by the visuals that are going on for what they are recording. And the reason I am mentioning these differences is because I found when I first started recording, I had to adjust how I was perceiving sound. I had to think about it in terms of how a microphone is going to be seeing the signal source and not how my ears are hearing the signal source. This is really important to understand when you're thinking about placing microphones and choosing different microphones. And right before we get into the actual design of microphones, I want to go over two basic things about sound that I think is necessary for us all to understand. First off is the inverse square law, and this states that the intensity of a sound is proportional to the inverse of the distance squared. So if we were to have a sound source with a microphone at distance d, and we doubled that distance, we are looking at a fourth of the intensity. In terms of dB, we're looking at 6 dB in reduction for every distance that is doubled from a signal source. Really important to understand. The second thing I want to talk about is diffraction, and this is something that doesn't seem to be talked about a lot when it comes to sound, and I think it's a really important principle to understand before we move on. Think about how light reacts when it is sent through a prism. The different wavelengths of light are separated in different directions. So sound also reacts in a similar fashion for different wavelengths or frequency of sound. Let's say we have a signal source here, and it is projecting sound across this wall. And there's a corner of this wall here. The higher frequencies, they're not going to be affected very much by this wall. The lower frequencies, however, are going to round this corner a bit, and the lower you go, the more rounding you are going to see. And this is important for a multitude of reasons. The first reason is that it is going to affect how a microphone is picking up different frequencies of sound. And secondly, it's going to affect how sound is moving around in the room. Let's think of a situation where we have a drum set. So here's a poorly drawn drum set. And let's just say we have a partition wall separating this drum set from, let's just say, an acoustic guitar that we want to record over here. And, you know, we have an extensive mic setup for this drum set, and we have another microphone that's going to be recording this acoustic guitar. Now, this partition wall might separate the high frequencies from the cymbals and maybe the attack of the toms and the drums, but those lower frequencies, they might travel around this corner and enter this microphone, and you need to be thinking about this in all situations. A quick way to test this phenomenon is put on some music and go to a part of the song where the drummer is riding on the cymbals and there's a lot of wishing and washing going on, right? And turn away from your speakers that are playing that song. Now with your hands, I want you to kind of bend your ears backwards and forward, kind of not allowing some of the sound from entering your ears. And you're going to see when you do that, that the low frequencies aren't affected very much at all from doing that. Those lower frequencies are coming around your head and entering your ears, while those higher frequencies, that cymbal washing I'm talking about, you're going to hear the variations of that sound. It's going to sound like as you move your ears back and forth. I just think it's a fun little exercise to help demonstrate this phenomenon. Alright, that I think is enough background about sound. Let's finally get into the microphone design and construction, which is why you clicked on this video to begin with probably. There are two major classifications of microphones that are going to be used in the recording studio, and that is dynamic microphones and condenser microphones. And I know what you're thinking, Mario, you forgot ribbon microphones. But really, what we think of dynamic microphones are actually called moving coil microphones, and ribbon microphones actually work on similar principles that a moving coil microphone works on. Dynamic microphones are going to work on the principle of moving a conductor through a magnetic field in order to induce an electrical signal. On the other hand, condenser microphones are going to work on the principle of a capacitor or a condenser, same thing, where the distance between the capacitor plates is going to be used to create differences in electrical voltages and subsequently the signal. Let's start off by going over the design of a moving coil microphone. Okay, so this is a very basic diagram of how a moving coil microphone works. At the heart of it, we have a diaphragm that is connected to a coil of wires that is suspended between a magnet. And this coil of wires that is wrapped around this cylinder is going to have a positive end of the wires and a negative end of the wires. Now, when this sound source here is going to be hitting this diaphragm, it is going to be moving it back and forth due to the pressure variations in the air. And when this coil is being moved through this magnetic field created by this magnet, it is going to create voltage differences between this microphone. And we're going to be seeing this in the form of an AC signal. Because this moving coil setup is relatively heavy, these types of microphones don't have a lot of sensitivity to the sound pressure waves. And because of that, moving coil microphones often have a very colored representation of the signal source they are recording. Now, a ribbon microphone is going to work on a very similar principle, where you're going to once again have a magnet, and between that magnet is going to be a thin strip of metal. And on one side of the strip of metal is going to have a negative lead, and the other side is going to have a positive lead. Now, when the acoustical energy from the sound source hits this ribbon of metal, it is going to flex it back and forth. And by flexing through this magnetic field, it is going to once again induce a voltage within these two wires as an AC signal that we will use as an electrical audio signal. And in reality, this strip of metal is extremely thin because it needs to react to sound pressure, and it is usually a corrugated piece of metal for strength. And since the resistance of this piece of metal is so low, there is usually a built-in transformer in a ribbon microphone that converts the impedance of the AC signal to something that is usable. Now, moving coil microphones are also going to see transformers sometimes in their design, but for a ribbon microphone, it is going to be crucial in order to get any usable audio signal. In comparison to a moving coil microphone, ribbon microphones are more sensitive to the sound pressure waves and are going to give you a more accurate sound to your signal source. Most ribbon microphones have a characteristic natural high-end roll-off that sounds very pleasing to the ears. Okay, now let's talk about the third major type of microphone that is going to be used in a recording studio, and that is a condenser microphone. And this is much different than how a moving coil and a ribbon microphone are going to be utilized. In a condenser microphone, you are going to have an external power source that is connected in series with a capacitor, which is the diaphragm in the case of a condenser microphone, and some sort of resistor. Now, this is a really, really simple circuit diagram for a condenser microphone. In actuality, it is much more complicated, but this is just to understand the basics. And let's just say, for example, we have 48 volts being supplied by this external source. We are seeing a 24 volt drop between this resistor and a 24 volt drop between the diaphragm. Now, as the signal source is transmitting acoustical energy throughout the air, the condenser microphone is going to allow the sound pressure waves to move this plate of the capacitor while this plate remains stationary. And by doing that, by moving this plate back and forth, that is going to alter the voltage difference between these plates, and subsequently, that is going to alter the voltage between this resistor. And that is how you get an AC signal of the acoustical energy. The electronics within a condenser microphone are going to be much more complex than a dynamic microphone. And this external power source is crucial to make this design work. You're either going to see this external power source in the form of phantom power, which is transmitted from your mixing board through your XLR cable, or if this condenser has vacuum tubes in it, you are going to see an external power source that is going to power the microphone. And that's most often seen in vintage style condenser microphones where vacuum tubes need higher voltages than is provided than the standard phantom power of 48 volts. Because condenser microphones have active electronic components, they are going to be much more sensitive to the sound pressure. And as such, you need to be careful when using these microphones up to a loud source. These microphones almost always have a built-in padding to take care of the preamplifier circuitry inside the microphone. Additionally, this heightened sensitivity is going to bring a lot more high end that could often be perceived as harsh, whereas a ribbon microphone is more known for a warmer sound that rounds off any of those harsh frequencies. The use of all three types of these microphones is going to be very situationally dependent. We should now understand how the three microphone types transduce that acoustical energy that we hear as sound in the room into a usable electrical audio signal that is then passed to our mixing desk. Now let's talk about directionality of a microphone, and this is another important characteristic of any microphone. Directionality is how this microphone is going to react to sound that is off axis. And what do I mean by off axis? Normally, when we think of a microphone, we think of pointing it directly at the sound source that we're trying to capture. In this instance, if I'm talking into this microphone, I'm going to be talking 0 degrees on axis to this microphone. But we need to consider the off-axis sounds. When I say off-axis, this would be 90 degrees off-axis. The sound coming from the back of the microphone would be 180 degrees completely off-axis. Turning it 90 degrees more would be 270 degrees off axis, and once again back to 0 degrees on axis. And microphones can come in 3 main types of directionality. The first being omnidirectional, the second being bidirectional, and the third being unidirectional. The first type of directionality we are going to talk about is called an omnidirectional microphone. And this means that it is not going to discriminate for sound coming from any direction. It is going to have equal sensitivity from sound no matter where it is coming in relation to the microphone. This is the basic construction of an omnidirectional microphone, where there is a diaphragm that is connected to a sealed enclosure. And this is also called a pressure microphone because it is going to react to pressure hitting this diaphragm. And in reality, this sound can come from any direction, like I said. I had someone ask me in a previous video, how does an omnidirectional microphone hear sound coming directly 180 degrees off axis? And this is actually a really good question, because although theoretically an omnidirectional microphone is supposed to be indiscriminate in relation to the off-axis sound it's picking up, there is some minor effect for off-axis sound. As you can see in this polar pickup pattern, it more accurately looks something like this, where there is going to be about a 5 dB difference of sound level from sound coming directly from the back of the microphone. And do not forget what I said earlier in this video about diffraction of sound wavelengths. And if the size of this omnidirectional housing is significant enough, longer wavelengths will pass to the front of the microphone, while higher frequencies might actually just bounce straight off the housing and not be picked up as sensitively as the lower frequencies. But I should make it clear that in practice, these effects aren't really seen. Omnidirectional microphones do act very close to how the name implies, that they pick up sound from all directions very evenly. Our ears function in an omnidirectional fashion. So if you want to see how an omnidirectional microphone reacts to a signal source, simply listen to a sound and turn your head and see how the sound reacts. You are going to notice that even if you are facing away from a signal source, the relative volume is very close to as if you were looking directly at that object. Now let's talk about bidirectional microphones, which are often referred to as figure 8 microphones for the reason of the polar response pattern. These are also referred to as pressure gradient microphones because they react to pressure differences on one side of the ribbon to the other side of the ribbon. And the reason for the dip in sensitivities around the 90 degree and 270 degree off-axis response of these microphones is because when sound is coming from, let's say, this direction, it is going to be reaching both sides of the ribbon at the same time, and they're going to be seeing the same pressure wave at said time. And this ribbon is not going to be able to flex in either directions, right? It is like you're pushing up against your fist with the same force. No fist is going to move in either direction. It is simply going to stay put and therefore not move the ribbon and subsequently create a electric signal. Something really important to think about when you're placing bidirectional microphones in a room is that depending on which side of the ribbon the pressure wave is going to be coming from, you are either going to be seeing a positive electric signal or a negative electric signal. If the pressure wave is going to the front of the microphone, that is when you get a positive voltage. When the pressure wave is coming from the opposite direction, this is going to give you a negative voltage. Now, the reason this is important is because it affects the polarity of your microphone signal. So let's think of a worst case scenario of what could happen if you're not thinking about this properly. Let's say you had two ribbon microphones right next to each other in a stereo setup. And let's say for one of the microphones, you had the front of the ribbon microphone facing the sound source, but you accidentally put the rear of the second microphone facing the sound source. When the pressure sound waves from your sound source hit both of these ribbon, you're going to see a different polarity of voltages from each ribbon microphone. You are going to be seeing a positive voltage from the first microphone while seeing a negative voltage from that second microphone. And when that happens, those two audio signals are going to cancel out completely, and you're going to result in no signal at all. Now, obviously, this is an extreme example, but this polarity issue can manifest itself in different ways in the studio if you're not thinking about the polarity of your ribbon microphone. And this second microphone doesn't necessarily have to be a ribbon microphone. It could also just be a moving coil microphone where the polarity of both these microphones are switched, and you're going to see the similar attenuation effects. Really important to think about. All right, the third directionality type we're going to talk about now is the unidirectional, or a phase shift microphone, or a cardioid microphone. All mean the same thing. And once again, the explanation I'm going to be showing here is extremely simplified just to understand the basics. In practice, unidirectional microphone designs are actually really intricate, and there's a lot of math that goes behind it. So at the heart of it, the diaphragm and housing system is very similar to the omnidirectional design. Instead, there are ports within the housing that allow air to enter from different directions. And this can be seen in a rear port design or even side port design. For now, let's just worry about a rear port design for this exercise. So when a sound is coming from the front of the microphone, it is going to hit the diaphragm, causing the diaphragm to move. And it is also going to travel around and come through the rear port of the housing. And the specific length that the second path takes in relation to the first path is designed to amplify that sound frequency. So in other words, the diaphragm is going to be seeing the signal from this first path as something like this. And because of this time delay that the second path has to take, it is going to be offset a little bit in time. But the mathematics that the designers of the microphone used made it in such a way the two signals will match with one another and amplify the signal. Now let's look at a situation where the sound is coming from the rear of the microphone. So that sound is going to come from the rear and is going to hit the front of the diaphragm as such. Additionally, it is also going to take a second path through the rear port of the housing of the diaphragm housing. And once again, the designers of this microphone made it in such a way that when these two paths hit this diaphragm, you're going to see cancellation. Something like this, where the two wavelengths are going to be completely out of phase and they will cancel each other out and not affect the diaphragm at all. Once again, I must reiterate, this is a very simplified version. I just want you to understand the basic concepts. In practice, the design is very technical and really interesting to read up upon if you're interested in that. And because of this phase shifting, you are going to see a pickup pattern like this for a standard cardioid microphone. There are also going to be a couple variations of this cardioid pattern, one being the hypercardioid, and another being a supercardioid, both showing different levels of off-axis rejection. Now, these pickup patterns can be combined with two different microphones to create different effects. For example, if you take two cardioid microphones, point them in opposite directions, and sum their signal, you are going to get an omnidirectional pickup pattern. If you do the same, but you subtract their signals from one another, you get a figure 8 pickup pattern. Now let's say you take that same cardioid pattern and you subtract the second cardioid pattern, but with an attenuated signal. You are going to get something like a super cardioid pattern. And there are ways to have multiple pickup patterns in one microphone. The first and easiest way is to have a cardioid microphone and have a physical way to block off the rear and side entry ports, thus turning it into an omnidirectional microphone. A really simple example of this happening is if you see a singer on a live stage wrap their hands around a cardioid microphone when they're singing, and now that microphone has turned into an omnidirectional microphone, and they might start to have feedback issues because now this microphone is not going to be rejecting sound coming from off-axis locations. Something that you do not want to do unless you're purposely trying to get an omnidirectional pickup pattern. Most people are going to be familiar with microphones having multiple pickup patterns in the form of a large diaphragm condenser microphone. And I want to go over this because I actually think the design and the method in which this works is actually very interesting. Alright, so I drew out a rough basic schematic of a large diaphragm condenser microphone that has multiple pickup patterns. And bear with me while I go and try to explain this, okay? And here is the power source. Let's just say it's 48 volts. These resistors here are going to break up that voltage, right? So we're going to have 48 volts here, 24 volts here, and 0 volts here. Instead of having just one diaphragm on this microphone, we are going to have two of them. The first being here, and the second one being here. And they are going to share a common plate that is stationary. So these two diaphragms are going to be moving back and forth in relation to the air pressure waves that are traveling through the air. Now this first diaphragm is going to be seeing this 48 volts. This common plate is going to be at 24 volts. So there's always going to be a 24 volt difference. And we're essentially going to alter the behavior of this second plate to change the pickup pattern of the microphone as a whole. Now over here I have a switch that controls the behavior of this second plate. There's going to be 4 different positions that this switch can be in, shown by this dotted line here. The first position is going to be a cardioid pickup pattern. The second position being an omnidirectional, the third being a bidirectional, and the fourth being some variation of a hyper or super cardioid pickup pattern. And I want to go through the 4 different positions to explain how this works. So let's start with the first position where the switch is connected to nothing, and this second diaphragm is not seeing any voltage on it at all. It is not being connected to the circuit, it is basically being suspended in air. The microphone is acting as a single diaphragm condenser microphone, and the housing is going to be designed in which this acts as a cardioid microphone. This is of course the easiest to understand. It is simply one single diaphragm reacting to the air, acts as a cardioid microphone. Very easy. Now let's see what happened when I put that switch in its second position. Now this second diaphragm is going to be seeing that 48 volts, and there's going to be a difference of 48 minus 24 volts of this plate, so 24 volts. So now both of these microphones are seeing a positive polarity of 24 volts in relation to this common collector plate here. Remember the situation I described before of having 2 microphones with cardioid pickup patterns pointing in opposite directions of one another right next to each other. They combine to be an omnidirectional microphone, and that is what this is acting as. It is essentially acting as 2 separate microphones combining their cardioid pickup patterns to result in an omnidirectional pickup pattern. Instead of needing 2 microphones, you're simply just doing it all in one housing. Now let's go to the third position. Now this second diaphragm is going to be seeing 0 volts on its plate. The voltage differential between this diaphragm and the common collector plate is still going to be 24 volts. Instead, it is going to have an opposite polarity of the first plate. This is going to be the second situation I described, where you're combining two separate cardioid microphones, but you're reversing the polarity of one of the microphones. When those two pickup patterns combine, you are going to get a bipolar pickup pattern, or bidirectional pickup pattern. And finally, let's go to the fourth position. Now, this second diaphragm is going to have a slightly higher voltage than 0 volts because there is a resistor here. And let's just say, for example, it is now 10 volts. 10 volts being seen by this second diaphragm. The differential between the first diaphragm and the common collector plate is going to be, once again, 24 volt differential. But now, the second diaphragm in the common collector plate is only going to be seeing 14 volts. That is basically the third situation I described, where you have one bigger cardioid microphone pattern and you're minusing a second cardioid microphone pattern. And you're going to get something like a hypercardioid or a supercardioid. And you see this set up a lot with large diaphragm condenser microphones, where there is a physical switch on the microphone housing where you could cycle through these different settings. Now, here's where things get really interesting. Let's say we got rid of this switch. So now we have this second diaphragm in series with a resistor here. And here's where things get really fun. Let's just say, for example, we made this resistor have infinite resistance. If we did that, this second diaphragm would not allow any voltage to be passing through. There's infinite resistance here, and this would be acting as if this second diaphragm was not there at all, and it'd be, in this microphone as a whole, would be acting as a single cardioid pickup pattern. Now let's see the opposite situation. Let's bring this resistance all the way down to 0. That would be as if this diaphragm was back to 0 volts, which would be a bidirectional pickup pattern as we described before in the third position. So because of this, we can vary the resistance of this resistor, which affects the voltage of the second diaphragm, and theoretically there's an infinite amount of pickup patterns that you could cycle through if you have a variable potentiometer here. And you see this a lot on high-end large diaphragm condenser microphones with an external power supply. They have a potentiometer to do exactly that. Really interesting stuff, very fun to fool around with. Unfortunately, I do not own a condenser microphone, but we will get there one day. Alright, so we're almost at the end of this video, but I need to mention two more effects that are seen with microphones. The first we're going to talk about is off-axis frequency response. Let's go back to the conversation about directionality in a microphone. In a cardioid microphone, if you remember, it is going to reject some sound coming from the off-axis directions. In actuality, due to the design limitations of microphones, the off-axis frequency response is going to change depending on the frequency of said wavelength. For higher frequencies, the cardioid pickup pattern is going to stay true, but as the frequencies drop, the cardioid pickup pattern is going to slowly turn into an omnidirectional pickup pattern. This effect is going to be more pronounced in inexpensive microphones, whereas the higher end microphones are going to be designed to minimize this effect as much as possible. But this is really important to think about, because you can be in a situation in your recording studio where this off-axis coloration can affect your end result. Alright, so let's say you're in a situation where you have a grand piano in one side of the room, and you're trying to simultaneously record this piano and a guitar as some sort of duet system, right? And let's say you think logically, okay, for the microphone that is on the guitar that I'm trying to record, I'm going to use a pickup pattern that is going to ignore the sound coming from this piano. So I'm going to pick a cardioid pickup pattern. Now, I'm speaking in all theoreticals here, but let's just say that this off-axis frequency response is able to adequately reject half of the frequencies coming from this grand piano. But the other half is being heard fully by this cardioid pickup pattern, because at those frequencies, the microphone is more acting as an omnidirectional microphone. Now, the signal that you're hearing from this microphone that you're supposed to be picking up this guitar, you're going to be hearing a distorted version of what this piano sounds like, right? You're going to be hearing just the low tones and not the high tones. Now, this might not be ideal. I mean, it probably isn't going to be ideal. And instead, you might have, keyword might have, been better with using an omnidirectional microphone here, where the bleed coming from this grand piano is going to be heard uncolored or undistorted, so to speak, from this microphone. So yes, you are going to be hearing this piano, but it's going to be at a lower volume, and it's going to mix well with the other microphone that is being used to pick up this grand piano. Hopefully I made sense there, why off-axis frequency response is very important, and why an omnidirectional microphone might actually be better if you're trying to ignore the sound of an instrument you're not trying to record. It is really situationally dependent, and there's no set rule of what you should do in given circumstances. Okay, the last effect that I'm going to mention in this video is the proximity effect. And I'm not going to go into extreme detail here because I want to do a whole dedicated video on this topic because it is very interesting. The physics behind it is very interesting, and there's some videos that I see online in some posts in some forums that actually talk about this in an incorrect fashion, and I want to bring some clarity. The basics that you need to know, though, is the proximity effect is an increase in bass response as a microphone gets closer to its source. Here is a quick chart showing how the distance can affect the bass response of a microphone. This effect is going to be most pronounced in ribbon or bidirectional microphones. In cardioid microphones, you are going to hear it as well, but not to as much as a degree. And in omnidirectional microphones, you're not going to see this effect to any meaningful amount. Microphones can be designed to minimize this effect as much as possible. A great example for a microphone that I talk about all the time is the EV-RE series with the variable D slot, which minimizes this effect. There are also microphones that have a bass roll-off switch that you could turn on if you want to close mic a sound source, and you don't want the effects of the proximity effect. And the proximity effect can either be a bad thing in your studio, or you could use it to your benefit. It's really going to depend on the situation. If you want to accentuate the bass frequencies, then sure, make full use of that proximity effect. But if you want a neutral response of whatever you're recording, you need to be careful if you're getting too close to a source. Another important thing to remember, and this is especially true when you're recording someone speaking or singing, because the proximity effect is so dependent on the distance from the microphone to the sound source, if someone is moving back and forth naturally while they're singing or speaking, the bass response is going to fluctuate greatly by this distance change. And if you have a singer that is moving around a lot, you might want to think about either one, backing up that microphone so the proximity effect is not being seen, or two, moving to something like an omnidirectional microphone that minimizes the effect of the proximity effect. Alright everyone, I hope you all learned something today, and I didn't get too deep into the weeds with microphone design. I apologize if I made any mistake. I will try to correct it in the comments or description below if I misspoke. And I must mention, a lot of the information in this video I am taking directly from the Recording Studio Handbook, a book that I have mentioned before that I really like. And something that I really like about this book, as well as the purpose of this video today, is the basics are extremely important to understand. When you understand the fundamentals, you are able to make informed decisions in your studio. When I first purchased this book, when I started out recording, I was actually a little disappointed because it doesn't go into detail about how to mic specific situations. It didn't tell me how to mic a guitar cabinet. It didn't tell me how to microphone a voice, a bass guitar, a drum set, whatever the case may be. And I was looking for someone to tell me what to do. Instead, it taught me the principles of why I want to make decisions and not what decisions to make. And I'm really glad that I got this book and read through it multiple times and understood the fundamentals. And you'd be surprised, sometimes even the simplest stuff on the 4th time or 5th time reading this book, it kind of opens a new avenue in my brain and it makes me think about something that I haven't thought about before. And that is why with this video, I'm just trying to go over the fundamentals, and even if you know a lot about microphone design, maybe it taught you something new. Alright, hopefully I did a swell enough job. Let's try to talk about some of these concepts in the comments, maybe talk about some of our favorite mics, whatever the case may be. I always love when we start talking about stuff in the comments, and I think about stuff that I haven't thought about before. Alright, everyone, have a good night.